Hello, everyone. I hope you are having a wonderful day. Thanks for joining my presentation. My name is Zhicong Ma, and today I want to share you what I learned about wildfire contribution factors in Santa Catalina Ranger District. If you don't know where that is one of the most visited routes for the Mountain Lion and the Coronado National Forest. So first and foremost, why did I say they are contribution factors? Some of you recently in South Arizona may already notice that you frequently receive the fire weather alerts in the last couple of weeks. Saying the risk of having wildfire is high. You can also see that on the little bear sign near the entrance of every national park. These alerts are sometimes not an overreaction. From the timeline I show you, massive fire have happened in the last 20 years within Santa Catalina Ranger District alone. Each time, the media and experts will explain what triggers the fire and why it gets so big and hard to contain. But most of the time, the reasons are pretty general. In this case, I want to dive deeper into those mentioned factors to see if they are critical to initiate and develop a wildfire. I'm using the data of the Zhicong fire. Let's get started. The first step of my project is to define a specific study area. It helps me to acquire data accordingly and makes the visualization process much more manageable. There are multiple elements taken into consideration. All contribution factors with great variety. The reason for excluding the neighborhood is to increase the accuracy of supervised classification, which we will cover later. And here's the actual study area, and its coordinates are listed as well. So you can take a look about where the location is and what the study area actually looks like on the map. Then we come to the workflow section, which lists down how the entire project progresses. First, we need to know the fire scale of the Zhicong fire. Then we need to compare the land covering change to find out which vegetation fuels the fire. Finally, I will evaluate other factors using GeoDA spatial regression models. Then we come up to assessing the fire scale using change of normalized burn ratio and raw satellite image. To calculate the NBR value, the data I use for this process is Landsat Level 2 surface reflectance product from the Earth Explorer. The spatial resolution is 30 meters. 2 days of data are acquired. I chose May 29th as my before the fire date, and August 1st as my after fire data acquired date. The principle of choosing the date is to have minor obstacles with little to no cloud covers. In this case, I can get the most realistic surface reflectance without the worry about the cloud. Also, to measure the scale of fire using a raw satellite image, I use SOMI MPP to acquire a high-resolution satellite image showing long smoke for the study area. Normalized burn ratio is a value that determines burn area and burn severities. It is calculated by the near-infrared and shortwave infrared band of the Landsat product. The formula is shown below. The formula is for the Landsat A data we are using. The figure below shows the NBR value around the 2008 around the study area on May 29th, 2020, using the ratio between the near infrared and shortwave infrared. A high NBR value here indicates healthy vegetation, with a low value indicates a bare ground or unhealthy vegetation. As elevation goes up, we can observe more and more healthy vegetation shown in the white or lighter color. This gives an initial look at the study area and get us ready to compare with the post-fire map. On the post-fire map, a large portion of study area quickly turned into the dark color compared to the previous map. Extremely low NVR value here means burnt ground. With most dense vegetation gone atop the mountain, only a few bright, healthy vegetation left. You can see around here, I believe. Basically on top of the summit. This map shows us where the major burn happened, but it's rather hard to say the scale of the burn and severity. To better understand that, we need to use the pre-fire minus post-fire to get the change of NVR map. And here it is. The burn severity is shown by the difference between the pre and post-fire NVR values. Actually, specifically is pre minus post. In this figure, flash red means burned where the burn had happened, and dark green represents vegetation regrowth. In this case, we're only focusing on the higher value of changed NVR. Most of the bottom lands remains unchanged, but the Zhicong fire's overall scale is depicted vividly. The light burns occurs at a lower level, but soon return to the worth noting scale when it reaches the top, which means scope and vegetation could be accelerating factors for the Zhicong fire development. We'll figure that out in the regression model portion later. Besides a change of NVR, the visual effects of the fire can also tell us about the fire scale. For example, by measuring the distance of traveling smoke, we can have another concept about the fire. Well, actually, the furthest distance that smoke had traveled is 63.84 miles. That makes the Zhicong fire not a local scene anymore, and I will explain why. By using the measurement tool in ArcGIS Pro, the raw satellite figure shows a record 63.84 mile long smoke extending to the Wilcox area, which is east of Tucson. It's far away from the Santa Catalina Ranger District. Heavy smoke could bring ash and debris into the air and cause poor air quality for Tucson and surrounding residents' health. Also, the smoke conducts Gallery wilderness area, which brings potential fire hazards to the surrounding forest because sometimes smoke also contains not fully burned ash, which could also ignite the next burn. As the scale of the fire is clear, now an investigation about which type of vegetation fueled the fire most is underway. First, I use NDVI as identification figure for each land cover. The near infrared and red band from the Landsat surface reflectance product is used. The formula is shown here. Like the NVR map, the NDVI map also shows vegetation conditions in the study area. A high value means greener vegetation, while low value means bare ground or unhealthy vegetation. Here's the pre-fire map. You can see a group pattern of vegetation on higher elevations, just as the NVR map have already shown. For the post-fire map, you can see the vegetation loss more clearly than the NVR map, since it has distinctive contrast between burned and unburned vegetation. To differentiate different land cover, I have divided land cover into three types: the bare ground, sparse vegetation like shrubs, and moderate vegetation like pine and oak. From trustable sources like USGS and EOS, I roughly limited bare ground to being less or equal to 0.1 NDVI. Shrubs roughly around 0.3, and pine and oak roughly around 0.5. Next is to set up training samples. I have 10 samples for each class in the training sample manager, and try my best to distribute them to all of the study area. The supervised classification is set to classify with maximum likelihood to the preset samples. And here's the outcome. After setting the training sample all of the study area, the supervised classification recognizes a wide distribution of sparse vegetation like shrubs, with little to no dense vegetation at lower elevations where the climate is too dry to survive. Plus, this figure corresponds to the initial argument about the vertical change of vegetation type around the study area. This evidence proved the relative accuracy of the defined algorithm for the three untapped categories. For the post-fire classification, the figure implements an explicit but different scene. A wild expansion of the bare ground categories, since many of the vegetation did get devastated during the Bighorn fire. A lot of the sparse vegetation disappeared in the flame and left with the bare bone soil. And the mark of the how wildfire surrounds the last bit of the pine oak is pretty impressive. By far, the classification for 2 time periods had already been complete. And that means it's time for a post-land cover change detection about which vegetation lost most population and which vegetation fuels the fire. Indeed, the combined tool is used to mix up 2 classifications with the same scheme. With scheme, I'm talking about classification scheme. The outcome is shown in the unique value symbology. For visual performance, I set the shrubs to bare ground blue and pine oak to bare ground red. This pine and oak loss mainly located on top of the summit, and shrubs loss is all over the place, especially where elevation is lower. There seems to be more pine oak loss from the map than the shrub loss, right? But is that really the case? I made a matrix to find out. The table shows land cover change before and after the Bighorn fire. Most of the shrubs remain unchanged. Those changed mainly turn into the bare ground after the change. Pine and oak categories are largely converted into bare ground. In the form, there is no value shown on change that represents bare ground to any vegetation. Over 12% of the area shown in the image changed from shrubs to bare ground, and about 7% of the area turned from pine oak to bare ground. In this case, even though pine oak lost most of the vegetation in terms of number, shrubs fuels the Bighorn fire to a massive extent. As we want to know whether spatial factors mentioned earlier can contribute to the Bighorn fire, I want to introduce spatial regression models in GeoDA, since space can act as a reasonable proxy for those factors we usually cannot but should include in our model. Let's do it. First and foremost, a user-defined daytime climate data from National Weather Service will be acquired for May 29th. The advantage of using this data set is they can collaborate with elevation change, which is helpful when accessing the when assigning location with varied wind speed, temperature, humidity according to the elevation. Beyond that, to receive slope and elevation data, I use 30-meter DEM from the Earth Explorer. Secondly, data preparation is required to import the ArcGIS file into GeoDA. Land cover is covered based on how dense the vegetation is, and a pending join tool helps to integrate all the data into one single feature class. Then the feature class is vectorized into the appropriate format GeoDA could recognize. In the GeoDA, a rock weight file is created because it has better performance on square-defined vectorized data, which is suitable for polygon vector we created. OLS and GWR are avoided for the choice of the regression model because the humidity, slope, NBR, and NDVI and other positive and other factors are positively autocorrelated and not normally distributed. The possible interference from those factors can lead to a biased result. In this case, spatial error and spatial lag models are chosen. Their R-square and likelihood and the AIC value will be compared to get the best model as possible. Spatial error model is preferred because it has greater R-square and log likelihood and smaller AIC than spatial lag model. All variables except NDVI are considered statistically significant, but the variables have coefficient correspond to the expectation. The coefficient of spatial correlated errors has a positive relationship and is highly significant, which indicates improvements of the model fit compared to the original spatial lag model. Unfortunately, the spatial effects still exist according to the last 2 test results. To fully illustrate my finding, I'm going to import Aspen fire data in the future with same analysis. I'm then checking out if those contributing factors have a similar relationship to the wildfire. I will find corresponding Also, to make classification more concise and accurate, tests will be run. So there's what I got from my project. Shrubs are certainly one of the primary fuels for the Bitcoin fire to expand due to its abundancy. At the same time, topological factors like significant slope will help ignition as fresh air climbing up. Even worse, South easy weather in May and June can make wildfire expansion accelerated and being harder to contain. Consequently, all mentioned factors can make Bitcoin fire grow and severely burn in the Santa Catalina Ranger district. Thank you so much. Any questions?